Talk will be organized as follows. I'm going to go over an introduction, like what is data assimilation. I will then go into the notation that I'll use for the remainder of the talk. And then I'm going to talk about just a very, very simple 1D linear problem for data assimilation. I find that this provides like a really nice foundation for the more complicated techniques that I'll talk about later. We'll also extend the 1D problem to multi-dimensions, because obviously oceans are not a 1D problem. And then I will finish by talking about sequential methods. So specifically, we'll talk about Kalman filters. And then I will talk a little bit about variational methods, which are smoother methods for data assimilation. Okay, so what is data assimilation? We all probably have like a basic idea of what it is, but basically we aim to combine any available information, this is your data, with a numerical model, while importantly taking into account any possible uncertainties. So like this picture describes, you have some previous forecasts that you have observations that can correct it, and you want to take those observations into account to produce something like this red line, which is like your corrected prediction for the estimate of whatever you're trying to observe. And so what can one do with data assimilation? So I'm going to give 3 different examples. This is by no means like an exhaustive list of everything that we can do with data assimilation, but these are just 3 interesting ones in my mind. The first one is weather forecasting. So every time you open your phone to look at the weather forecast for the week, this is a data assimilation problem. It's specifically a initial value problem. So the goal is to improve your initial conditions to get you a better forecast for the days to come. And this is just the output from NOAA weather for the weather in Austin. So as you can see, I have like 5 days. They're all kind of this plot. And this is also the precipitation forecast for the US a couple weeks ago. So this is a really common example of data assimilation that we just see every day. We can also do improved ocean state reconstruction. So this is probably really important for climate change. What I have here is a figure that reconstructed from 1992 to present, the ocean heat content changes. This is a product of the NASA ECHO project. So specifically, we took observations from satellites and various ocean measurement devices, including things like CPDs and Argo floats. I understood you guys have heard about Argo floats by now. And we reconstructed what the ocean heat content is over time. And you can really explicitly see that it's just kind of increased. And this is a really good indicator for things like climate change. And then the final example of data assimilation I have was one that I recently learned about, and I thought this was really fun. So basically on the sun, we have these things called sunspots. These are points of really high energy, and they happen on about an 11-year cycle. So they occur the entirety of the 11 years, but over every 11 years, we hit this peak where suddenly they occur much more frequently. We're currently in sunspot cycle 25, and scientists have recently started to use data assimilation to try to predict what the peak will be, how it will compare to prior sunspot peaks, as well as like when we can expect it to decrease, like when this will start to go back down. This is an interesting fact for scientists because it affects things like space weather, which can impact satellite lifetimes in orbit. But sunspots also end up resulting in things like this, which is the aurora. And so when you see the aurora, this is due to the particles that occurred when a sunspot happens on the sun. So those are just 3 examples of where we use data assimilation science now. But there's plenty more examples, by no means an exhaustive list. So now getting into the actual data assimilation. So there are 3 key pieces to data assimilation. The first one is your data, obviously. Second piece is your numerical model. And then the third piece are your uncertainties. So these can occur in both the data and the numerical model. And when I get into the methods, you'll see that these are really important for actually doing the data assimilation. So talking about the first ingredient, this is your data. And since this is an ocean school, I thought this was a really fun example of where we get data in the ocean. So this is a seal. And specifically, seals are used for measuring temperature at depth. So the heat transfer from the lower to the upper layers in the ocean is not a fully well understood physical process, but seal data can help us understand that because seals, as they go about their natural lives, take swims really, really deep in the ocean. And as they take their really long dives, they have this little instrument on their head that collects data for science to use. And I thought that was a fun use of seals for data. But they're just one example of where we get data in the ocean. So there's a plethora of satellites that collect data on things like sea surface variability. We also have GRACE and GRACE follow-on, which measure the gravity field. So this is like mass changes in the global. So these can help with things like ice loss. We also have things like these CPD instruments that stands for conductivity temperature at depth. It measures the exact thing. You've probably heard by now about Argo profiling floats. We also have instrumented moorings. So this is where scientists go on actual expedition. They drop an instrument into the water, collect the data, withdraw the instrument from the expedition. And then we also have ice tethered profilers. So these are instruments that are actually connected to the ice and collect information on water content in the Arctic. So there's a very large variety of ways that we collect data in the ocean, and then we want to know how to assimilate that data. So the second ingredient is the numerical model. So this is kind of like the backbone of data assimilation, right? The numerical model represents a time-evolving state via the equations of motion, conservation laws, etc. It's a really complex system. They're usually solved on something like this. This is the supercomputer at UT Austin. This is specifically Stampede. And yeah, so there's actually a Stampede. And the state consists of coupled variables. So for the ocean, these can be things like temperatures, salinities, and velocities. And like I said before, it really is just a very complex, multidimensional system that we try to solve on our computer. And so the final ingredient in data assimilation are your uncertainties. This is kind of like the focal point of the summer school. So nothing is ever going to be perfect. These seals are not swimming through the ocean with the intent of finding you the best possible temperature data, and we'll always have uncertainties in both the data and the model. Some of the sources of uncertainty in your data, these can be things like data sparsity. You can either have spatially sparse data or temporally sparse data, or in the case of the ocean, it's usually both. So spatially sparse is exactly what it sounds like. We just don't have a lot of information for a given area. So like in the Arctic, it's supposed to be covered by ice. We can't collect a whole lot of data there. We can also have temporally infrequent data, so it doesn't occur very often. So like if we collect data every few months rather than very frequently. You can also have incomplete data. So our models are really high dimensional, and you can have data on part of the state vector, but not all of the state vector. You can also just have measurement errors, so things like noisy data. And then there's also uncertainty in the models themselves, right? And one of the big ones is that we have the model discretization. So the ideal solution to a system of PDEs would be a continuous function, but when we solve it on a computer, we're going to discretize. And so when you discretize it, you're only ever going to get an approximation of what the model solution should be. We also can have sources of uncertainty in the boundary conditions in your model. So there are scientists who want to study things like ice sheet sliding, so sliding ice sheets. And one of the things that really impacts how an ice sheet slides would be its bottom topography. We can't know what the bottom topography is perfectly, and so you're going to make some assumptions. This is another introduction of uncertainty in the model. You can also have uncertainty just in the model parameters themselves. So this can be something like viscosity. We don't have a perfect example of viscosity of ice. It's only an approximation. And so as you can see, there's a lot of different ways that uncertainty can enter the picture through data assimilation. And so what can we do? So importantly, data assimilation will take into account both the model and the data uncertainties. And what we'll see is that this will produce the best possible estimate given the data that we have. So you're always going to want to compute the model estimate and statistical info on sources of uncertainties. So now getting into the notation that I'm going to use, and I'm also going to introduce a couple of statistics definitions. So I'm going to routinely use X to define the correct model state, or what we're trying to approximate with data assimilation. I'm going to add a tilde. This will be our model prediction. So this will be what we want to estimate X. Y will indicate a data or an observation, and N will be your observational error. Generally, these variables are going to be multidimensional, but we're also going to briefly look at a 1D problem. So these are the couple of definitions of statistics. I'm not a statistician. These are just going to be like a very heuristic overview of these definitions, but in order to talk about some of the data assimilation, I think it's important to at least see these. So, and you might have already seen them in front. We're going to let P denote a probability distribution, and we'll say Y is an observation of some quantity X, and it has its associated noise or uncertainty N. That'll be our observation, and we're going to let this capital E denote the expectation value. This is some functional. So the expectation value is just the expected value of a random variable N. So given a random variable, the expectation value tells you what N will be on average, given your probability distribution. And then the second definition I have here is the variance. So the variance is the expectation value of N minus the expectation value squared. It's the amount that N will vary around the mean. So it tells you something about the uncertainty in the random variable, specifically for data assimilation. Okay, so getting into the first example, so we're going to do a least squares linear estimation. So let's say that we have some unknown quantity x, but we have two observations of x. So we have y1 and y2. They each have their associated noises n1 and n2. And we're going to make some assumptions about what we know about n1 and n2. So the first assumption that we're going to make is that we have unbiased observations. So we expect that on average n1 and n2 are 0. This is just saying that the noise in my observations is not really skewed to be super large, and it's not really skewed to be super negative. It's on average around 0. So like I said, we're going to make assumptions that we know what the variance of the noise in both of our observations is. And if you're working with like a toy problem and you have some Gaussian distribution, you can know what this is exactly. In the real world, that isn't the case for one of these assumptions on the and then the final assumption that we'll make is that the observational errors are uncorrelated. This is just saying that given some known information about N1, it has no bearing on what N2 is. They're completely unrelated to one another. Okay, so a linear approximation given these two observations would look something like this. It'll be x tilde is equal to some weight A1 times Y1 plus some weight A2 times Y2 for some currently unknown weights A1 and A2. And so that kind of tells you where we're going to go. And to figure out what these weights are, we're going to minimize the model data misfit of something called like a loss function or a cost function. And we weight each term in the model data misfit by 1 over the variance of the correlating observation. This is just the squared L2 norm for those who are familiar. So then when we want to minimize a function, we all know what we do. We take a derivative and we set it equal to 0. So taking a derivative of that loss with respect to the variable x, we just get something that looks like this. And expanding it out, you get this function, right? And then we set it equal to 0 and solve it for the quantity that we're looking for. And that tells us precisely how to weight these observations y1 and y2. Specifically, we get these weights. If we just pull them down to that equation, we get sigma 2 squared over some number for A1, and we get sigma 1 squared over some number for A2. And importantly, we kind of notice that for the weight on Y1, it's looking at the uncertainty on the second observation and vice versa for A2. And this actually works out really nicely. So I have this little picture here, and I've tried to emphasize that the uncertainty on Y1 is much larger than the uncertainty on Y2. And so what ends up happening is when we're waiting to find this value x tilde, we know that y2 is a more certain observation, so we want to get it a bigger weight. And so we weight it by the sigma 1, which is exactly what we have here. Or we weight it by sigma 1 squared, but and then we know that y1 is a more uncertain observation, so we weight it by the smaller uncertainty, so we give it less power in the overall assumption capability. And so this ends up working out really nicely. And this will be, and I think it's also just really important to note that if we didn't know what these variances were, this would be a much harder problem. And then I also wanted to point out, just to kind of emphasize that we're really finding like the best possible estimate for this x-tilde. So you can actually find it through a different minimization. So before we minimize a model data misfit, if we add to those statistical assumptions that x-tilde is an unbiased estimate, so this means that it's on average going to be the same value as what we're looking for. It's the expected value of x. And then we can minimize the variance in the actual observation. So we can minimize this expectation value, and you will find the exact same weights A1 and A2, and we will see that we're actually finding the approximation of x tilde, or sorry, the approximation of x with these weights that minimizes this uncertainty, which is, I think, kind of. So as we know, oceans are not 1D, so all of this can be shifted to multi-dimensions. So now in this case, we have some vector y, which will be our observational. We have a matrix here called E. So E distributes the entries of x that have observations. So we might not have observations for all directions of x. We might only have them for some. And then we add on this noise vector. We're still going to make the same assumptions regarding the noise. So we'll still expect that on average n is 0. And we assume that we know what R is, which is this covariance matrix. R is in general symmetric, and because we assume that the observational errors are uncorrelated, it actually ends up being a parameter. And then the loss function in multi-dimensions is exactly as it was before. It's this inner product weighted by the 1 over the variances, which is exactly what R is. So we're doing the exact same process with this new loss function. We can find x tilde again. So we take a derivative of it with respect to x. This first step is just the product rule, okay? The second term is a lot easier to find because we don't have these transposes to deal with. But if we You can either look up like matrix vector derivative rules, or you can do like Einstein notation. What this ends up being is 2 times this transpose times R inverse E. We again set it equal to 0 and solve it for x, and it gives us this new approximation for x tilde in multi-dimensions. And it is again just a weighting of our observations by their uncertainties, or by uncertainties in general. Cool. And so this estimate that we just found is sometimes referred to as the blue. This stands for the best linear unbiased estimate of x from y. And since we know that it minimizes the uncertainty in the estimate, it really is the best we can do given y. And the corresponding uncertainty can be found through this expectation value. And this just ends up being this formula here. And I made these purple because I'm going to come back to them later when we talk about Kalman filtering. Okay. So getting into the first method, so we're going to move to being time dependent. It might be a little bit confusing, but in general, what this just means is that my state x of t depends on a specific time step. We'll also assume that we have the state transition matrix A. A is determined from the equations of motion, so this is how you take x of t to x of t plus delta t. The observations are now also going to be time dependent. And in general, we're just going to add an of t everywhere. So just say it depends on time. You can have cases where A depends on time. In Kalman filtering, what our goal is to assume we have some background estimate. So we have some x tilde of t, which is some approximation of this value x. It has its associated error epsilon. We have its corresponding uncertainty matrix, which is this p. It's this expectation value of epsilon transpose. And then we also have data or an observation at p plus delta t. And our goal is to combine all of this information to produce that best linear unbiased estimate at p plus delta t. So we're just going to find a way to combine x tilde and y. And that's what Kalman filtering tries to do. So the step 1 is to say, let's say we have an intermediate prediction. So like we saw, my data lives at time t plus delta t. What we had was a background. If we didn't have data at t plus delta t, the best thing that we can do is to just step the model forward using our numeric. So that gives us a background estimate. We've introduced this notation of a minus sign that indicates no data has yet been incorporated at time t. And then the second step in Kalman filtering would be to compute the associated uncertainty of this background estimate. It's again found just through an expectation value. And so just expanding this out, we get something that looks like this. And that tells us, because we know exactly what the expectation value of epsilon t transpose is. It was the uncertainty or the covariance matrix of the background estimate that we had. And that tells us how to find the uncertainty at time t plus delta t when we don't have any data yet incorporated. Okay, so we now have an estimate, x tilde of t plus delta t. We have no data yet incorporated. We have its associated uncertainty. How do we add the data y at time t plus delta t? So we're going to do this exactly as we did before with least squares linear estimation. So I'm going to list out a bunch of knowns just to kind of make things really clear kind of where we stand. So we have x tilde t plus delta t with no data. It's some approximation of x plus some noise. We have, this would really be a t plus delta t here. We have the observation y. It's some observation of entries of x plus its own associated noise. And then we have the 2 covariance matrices. So we have the covariance of the noise in this background estimate, and we have the covariance of the noise in our observation. And so our goal is to find this weight. I put it here as a little question mark of this now like block vector, such that we can combine x tilde and y to get the best estimate. And so we want to know what this is. And if you can kind of piece together what we did with that 1D problem, then multidimensional problem, we found what this was precisely. And so we're literally going to kind of plug and chug what we know E and R are for this block vector. So E is now going to be a block column matrix kind of thing, where the first entry is I and the second entry is E. The covariance matrix is now this on the diagonal. So we have P without any data. And we have R, which is the covariance matrix of the noise in the data. And we're just going to put this into what we found for the week. In doing so, we get something that looks like this. It looks a little complicated, and we're just going to completely like expand this out. And what you end up getting once you expand it out is something that looks like this. There is some matrix shenanigans you need to do when you do the algebra and actually get it in this form. But we get a whole big matrix multiplied by y minus e times x tilde, so by we kind of like model data misfit, added to x tilde without any data. And this weight is again really just a weighting of the uncertainty in both the observation and the background estimate with this matrix E, which just tells us where observations went. And so this is precisely the common gain matrix. So this is kind of like the part of common filtering itself. So we can also use that prior formula we found for the uncertainty in the multidimensional case to update what P of T plus delta T is. It was precisely this value, and I forgot to mention, I mostly just added underscores here to really emphasize that these are not the same as these operators, so different even parts. But if we just plug in what we found for E and R in that block matrix fashion, then we get something that looks like this. And you can see that we've improved the uncertainty. So we have taken what we found the uncertainty to be for the background estimate, and we subtract off what the common gain is times the times. So just kind of reiterating, so we are trying to weight x tilde and y together using what we know about the two values. So we know something about their error covariances. And we found what this question mark was before. So we are just creating these block matrices given what we know the block vector is. And that leads to an equation that looks like this, which we can actually expand out and do some algebra. And we ended up with the common gain matrix. So this is how we incorporate data with the common filters precisely by computing this full value. Okay. So, and then we saw that we can update the uncertainty, which is great. And then I'm only going to very briefly put these up here because I don't want you guys to feel like you need to memorize the equations, but the general gist of the common filter is to say, we integrate the model, we compute its uncertainty, and if we have data, we can then find this common gain matrix to update our estimate of what X would be. And then we can update the uncertainty. So this is kind of why, I think this is kind of why it's called a sequential method, because you can really see that it just happens sequentially. And so I have a little picture here of what the common filter is really doing. So like, let's say we start from some X tilde of T. So if we don't have any data, so all of these crosses indicate data, they have their corresponding uncertainty bars. If we don't have any data, then the common filter just integrates, say this is a line, we're just going to go along with the line as we know it. And then we hit the first data point, and the common filter will actually jump down to closer to where the data is. Since the uncertainty bar is kind of large here, we're not going to go directly to the data, but we'll go somewhere close-ish or somewhere better to it. We find this new estimate X tilde of T1. And then again, we don't have any data, and so we just integrate along until we do have data. And the common filter is also not great at knowing when you're close to the true value. So like if we look at this X tilde of T3, we're pretty close to this dashed line, which we can say is what we're trying to estimate. But then we have this observation that's farther away, and it doesn't really take that into account. And so it, again, moves farther from the true value, again, creating this jump. And when I say jump, I mean that quite literally. So I have here this figure. So this is a output from this paper. We reconstructed the energy of the system, and a greenhouse gas oscillator system, using the common filter. And all of these vertical lines indicate where there is data. So the blue line indicates the true value of, say, the energy. And then this yellow line, which is kind of overlapping with the red line, is the common filter and the prediction. And up until you have a data point, the common filter is just going to integrate the model using whatever assumptions you've made up until that point. And then you hit the first data point, and it actually creates like a whole big jump. And you get this thing that looks really choppy and is not really physical because the energy shouldn't be a discontinuous solution. And the same thing happens in displacement. But I feel like this is also really important to note because the energy is computed from the states. So the common filter, in the way that we've described it, is taking estimates of the state vector, but those discontinuities that occur in the data propagate through when you try to compute this diagnostic quantity of the energy. So this kind of hints that the common filter might not be great at reconstructing a state. It might be better for something like forecasting. When you're not worried about, when your only goal is to compute roughly what it is between the data points. So now I'm going to get into the second method that we use for data assimilation. So this is a variational problem now. You can also think about it as a smoothing problem. So our model data misfit becomes this new sum over all of the time steps. So we view each x of t and y of t individually. This is like a variational form of the model data misfit that we saw previously. Our goal is still going to be that best linear unbiased estimate, giving any available information y. And in variational methods, what we do is we're going to minimize this model data misfit under the constraint that x of t is equal to ax. So this is saying we're minimizing j under the equations in motion. And this is kind of a wordy way of describing it, but basically we're going to combine the available observations with the numerical model by doing a global adjustment of the model to observations. So previously in the Kalman filter, we really only adjusted our trajectory at the points where we had observations. And variational methods don't do that. We do a global optimization scheme. So the method that I'm going to use to minimize j is the Lagrange multiplier method. This is one of the ways that people view variational methods. The first step before even getting into that is to define our control variables. So in data assimilation, we need to optimize, like we said, we're going to optimize j, or what we'll see is we'll take a derivative of j. We need to decide what we're taking a derivative of j with respect to. This is kind of what we can adjust in our model to improve our model estimates, like a reconstruction. One of the common ones would be something like your initial condition, because the solution to your system is uniquely defined by your initial condition. You can also adjust for things like parameters, though. This is by no means the only option. But everything that I show moving forward will be that our control variable is the initial condition in the model. And so our goal, like I mentioned, is kind of we're going to use Lagrange multipliers, because this is a Lagrange multiplier method, to compute the derivative of j with respect to our initial condition. And so let mu denote the Lagrange multipliers. This defines for us our Lagrangian. So the Lagrangian is going to be this very large multidimensional problem. So it's individually dependent on x of t and mu of t at every point. It's the sum of our loss function or our cost function, model data misfit, plus the Lagrange multipliers times x of t minus ax of t minus delta t. And this is kind of where you can start to see that what the Lagrange multipliers do is they enforce our constraint. And importantly, the stationary points of our Lagrangian are going to correspond to the minima of our constraint optimization problem. So by finding the stationary points of the Lagrangian, we can subsequently find the minimum of our loss. And that's what we're going to do. So taking derivatives of our Lagrangian and setting them equal to 0, because again, this is the optimization problem, this will derive for us something called the formal equations. And we're going to take a derivative of our Lagrangian with respect to mu of t and x of t at every single time step effectively. So you get this big set of equations. The first set of normal equations after you set them equal to 0 looks something like this. This is precisely our equations in motion. And so this really helps emphasize like these Lagrange multipliers, what they're doing is they're enforcing our constraint. And so solving the set of normal equations or locating the x values where this is 0 tells us that we're satisfying the physical model. The second normal equation is at a specific time step. And I set this one aside because what it does is it defines mu of t for us. And this is like the Lagrange multiplier at the final time step. And so you can kind of think about this as we're doing like a forward run. And this kind of hints that we're going to start some sort of backwards run with these Lagrange multipliers. And that's precisely what the third set of normal equations does for us, is it defines a relationship between mu of t and mu of t plus delta t. So this gives us a way to backpropagate all of these Lagrange multipliers in time. And then the final normal equation is what defines the derivative that we're actually looking for. So once we found the x values and the mu values that set the value equal to 0, we can compute this. We'll get some value, right? This will be an approximation of the derivative of j with respect to x at t naught. And our goal will then be to use this in some sort of gradient-based optimization scheme to improve the initial condition. And all the while, we are really taking into account the uncertainties through the use of this loss function to be able to live at the site of j. Cool. And so that is like a very high-level overview of what variational methods do. In practice, you would do this numerically. So like I use multiplication. And so the step 0 in the variational framework is to define something like control variables. So you want to define what you can actually tune in the model to improve your estimate. Our first step is to define the control variables. This is what we can actually tune in the model. Our step 1 would be to locate the Lagrangian stationary point, which is to solve these normal equations. And then we would use the computed derivative and the gradient-based optimization scheme. So you would usually do this a few times. In ocean models, it's kind of expensive, so you only do it in 5 times or so. And this will help improve the initial condition. And once we have located close to where the stationary point is, we can reintegrate the model and we'll have a reconstruction. And so there's kind of one sticky point in using this technique for actually computing the derivative. So we need to take a full model derivative. That's quite literally what this means, because A is meant to encapsulate and can be a highly nonlinear system of equations. And you need to take a full model derivative of this with respect to the state. You could theoretically write this out by hand, but it would be tedious. I think that there are scientists that actually do this, though. I specifically, I think that a lot of people make use of something called automatic differentiation. This is a numerical tool for taking a derivative, and this is what I do in my work. Okay, so I have a sketch of what the variational method does, again, with the line, just kind of a cartoon. So you have your initial assumption for what this initial condition is, or whatever the y is. In this case, the y-intercept is. We would integrate the model forward, and after integrating the model forward, we have some loss, and we would use this variational framework for computing a derivative of our loss with respect to the initial condition, at which point we move the entire line down. So after doing our optimization scheme, and then we get a new estimate for what the initial condition is. This plus sign is indicating that we've used data both past and future. I guess since this is the initial condition, but only future. But we get a new line, and then we rinse and repeat this process until we get something that looks like this final line. It intercepts all of my uncertainty bars, and it's a good approximation for what the overall line is. So we've improved our initial condition. And so like I hinted at the beginning, you don't need to do this with respect to the initial condition. You can also use other control variables. So we can opt to define something else. So in these examples, we've got a line, x of t is nt plus b. We can also tune other parameters in the line. So we can tune things like the slope. So like, let's say we know roughly what the initial condition is, but we don't have a good estimate for what m is. You would use this exact same process to use these Lagrange multipliers to find a derivative, and then iterate your slope value until you get something that's close to the reconstruction you're looking for. So usually what happens is you'll get oscillating value. You can also do both of them at the same time. You can use the variational scheme to compute both the derivative with respect to the initial condition and the slope simultaneously. And in this figure, you kind of end up like skewing the line as you use your gradient-based optimization scheme. And importantly, one of the nice things about this is that when we compare it to the sequential methods, whereas before we saw these discontinuities at every point where there was a data step or whatever point there were data, and we get this like jump, the variational scheme doesn't actually do this. Because we're doing a global optimization process, we get a smooth result in the end. And then I have another figure here from the same paper. So in this case, we use both a smoother method and a sequential method, so the common filter, to reconstruct again the energy in the system. This was for a Rossby wave system. The yellow line here is the reconstruction that we get when we do common filtering. The purple line is the reconstruction we get when we do smoother methods. And if we look at the zoomed in photo, so this second figure is just a zoom in on all of the points where we had data, we precisely lost these discontinuities. So the result from the smoother method is smooth, as the name would imply, which makes it kind of a better choice if your goal is to do state reconstruction versus something like forecasting. Cool. So that is roughly what I have. So just some of the conclusions. So I hope that you've taken away that data assimilation really aims to combine observations, models, and their associated uncertainties. Depending on the application, you might want to use different methods of data assimilation. So forecasting might be better fit for sequential methods. If you're trying to do a whole reconstruction of a state, you would be better off maybe doing a smoother method. And I think probably the most important, especially since this is an uncertainty quantification summer school, is that the solution to your data assimilation problem really depends on the uncertainties that are provided for both the background state and the observation layer. And they play a really big role in what happens with your reconstruction.